Hi all, myself Nidhin V from first year Artificial Intelligence and Data Science Department from Sri Manakula Vinayagar Engineering College, Puducherry. Let us see the experiments from 1 to 8 of digital system design.
Hello everyone, we are going to see about the first experiment of digital system design, study of logic gates. First we can see the AND gate. This is the symbol for AND gate. Here 1 and 2 will be the input and 3 will be its respective output. So we can connect the inputs 1 and 2 the input and 3 is its output. So we should connect it. When the input is 0 and 0, the output will be also 0. When the input is 0 and 1, the output will be 0. When the input is 1 and 0, the output will be 0. When the input is both 1, the output will be 1. This is known as AND gate. So next we can see about OR gate. This is the symbol for OR gate. Here also the same 1 and 2 is input and 3 is its respective output. We can connect the inputs and the output. When the input is 0 and 0, the output will be 0. When the input is 0 and 1, the output will be 1. When the input is 1 and 0, the output will be 1. When the input is both 1, the output will be 1. This is known as OR gate. So we can see the third gate, which is NOT gate. This is the symbol for NOT gate, where 1 is input and 2 is its output. We can connect the input and its output. This is the input and this is the output. We should connect each other. When the input is 0, the output will be 1, and when the input is 1, the output will be 0. This is for NOT gate. So we can see the fourth gate, which is NAND gate. Here 1 and 2 is the input and 3 is its respective output. We can connect the inputs 1 and 2 and its respective output. We can connect it. When the input is 0 and 0, the output will be 1. When the input is 0 and 1, the output will be 1. When the input is 1 and 0, the output will be 1. When the input is both 1, the output will be 0. This is for NAND gate. So now we can see the fifth gate, which is 3 input NAND gate. So we should add one more input. So we should get 3 input 1, 2 and 3 and its one respective one output. When the input is 0, 0 and 0, the output will be 1. When the input is 0, 0 and 1, the output will be 1. When the input is 0, 1, 0, the output will be 1. When the input is 0, 1 and 1, the output will be 1. When the input is 1, 0, 0, the output will be 1. When the input is 1, 0 and 1, the output will be 1. When the input is 1, 1 and 0, the output will be 1. When the input is 1, 1 and 1, the output will be 0. This is for 3 input NAND gate. So now we can see the sixth gate, which is XOR gate. This is the symbol for XOR gate, where 1 and 2 is its input and 3 is its respective output. We should connect the inputs 1 and 2 and its output. When the input is 0 and 0, the output will be 0. When the input is 0 and 1, the output will be 1. When the input is 1 and 0, the output will be 1. When the input is both 1, the output will be 0. This is for XOR gate. So now we can see the seventh gate, which is NOR gate. This is a symbol for NOR gate where 1 and 2 is the input and 3 is its respective output. So we can connect the inputs and its output. We can connect it. When the input is 0 and 0, the output will be 1. When the input is 0 and 1, the output will be 0. When the input is 1 and 0, the output will be 0. When the input is 1 and 1, the output will be 0. This is for NOR gate. Now we can see the second experiment, which is study of adder and subtractor. First we can see the half adder. For half adder we need two gates. They are XOR gate and a AND gate. First we need to give two inputs for XOR gate and the output for XOR gate and another output for AND gate. We need to connect the XOR gate, two input to the XOR gate and the output from XOR gate. We need to interconnect the AND gate and another and give this. The first output is the sum and the second output is the carry. When the input is 0 and 0, the sum will be 0 and the carry will also be 0. When the input is 0 and 1, the sum will be 1 and the carry will be 0. When the input is 1 and 0, the sum will be 1 and the carry will be 0. When both the inputs are 1, the carry will be 1. Now we can see the full adder. The joining of two half adder is called as the full adder. To see the logic diagram of full adder, we need two XOR gate, two AND gate, and an OR gate. We need three inputs, 1, 2 and 3, and we need two outputs, one for sum and another for carry. One for sum and the other one for the carry. So we can join all the circuits. So we had joined all the circuits. So now let's check the output. When the input is 0, 0 and 0, the carry and the sum will also be 0. When the input is 0, 0 and 1, the carry will be 0 and the sum will be 1. When the input is 0, 1, 0, the sum will be 1 and the carry will be 0. When the input is 0, 1, 1, the sum will be 0 and the carry will be 1. When the input is 1, 0, 0, the sum will be 1 and the carry will be 0. When the input is 0, 1, 0, 1, the sum will be 0 and the carry will be 1. When the input is 1, 1, 0, the sum will be 0 and the carry will be 1.
When the input is 1, 1 and 1, the sum will be 1 and the carry also will be 1. This is known as full adder. So now we can see the half subtractor. For half subtractor, we need a XOR gate, an AND gate, and a NOT gate. We need two input and two output. For the output, one is for difference and another one is for borrow. So we can connect the circuits. We have connected the circuit. When the input is 0 and 0, the difference will be 0 and the borrow will also be 0. When the input is 0 and 1, both the difference and borrow will be 1. When the input is 1 and 0, the difference will be 1 and the borrow will be 0. When both the inputs are 1, both the difference and borrow will be 0. This is known as half subtractor. Now we can see the full subtractor. Joining of two half subtractor is called as the full subtractor. For this experiment, we need two XOR gate. We need two XOR gate, two AND gate, we need a NOT gate, two NOT gates, and a OR gate. We need three inputs and two output. One output is for difference and the other output is for borrow. So now we can connect the circuit. So now we have joined the inputs and outputs of the circuit, and now we can check its output. When the input is 0, 0 and 0, the difference and borrow will be 0. When the input is 0, 0 and 1, the difference will be 1 and the borrow will be also be 1. When the input is 0, 1, 0, the difference will be 1 and the borrow also will be 1. When the input is 0, 1, 1, the difference will be 0 and the borrow will be 1. When the input is 1, 0 and 0, the difference will be 1 and the borrow will be 0. When the input is 1, 0 and 1, both the difference and borrow will be 0. When the input is 1, 1 and 0, both the difference and borrow will be 0. When the input is 1, 1 and 1, both the difference and borrow will be 1. So we had looked the full subtractor. Now we are going to see the third experiment, design and implementation of code converter 1. From there we can see binary to gray conversion. So for that we need 4 inputs, 4 outputs and 3 XOR gate. We can connect the 4 inputs. We had connected all the inputs. Now let's check its output. When the input is 0, 0, 0 and 0, the output will be 0, 0, 0 and 0. When the input is 0, 0, 0 and 1, the output will be 0, 0, 0 and 1. When the input is 0, 0, 1, 0, the output will be 0, 0, 1, 1. When the input is 0, 1, 0, 0, the output will be 0, 1, 1, 0. When the input is 0, 1, 0, 1, the output will be 0, 1, 1, 1. When the input is 0, 1, 1, 0, the output will be 0, 1, 0, 1. When the input is 0, 1, 1, 1, the output will be 0, 1, 0, 0. When the input is 1, 0, 0, the output will be 1, 1, 0, 0. When the input is 1, 0, 0, 1, the output will be 1, 1, 0, 1. When the input is 1, 0, 1, 1, the output will be 1, 1, 1, 0. When the input is 1, 1, 0, 1, the output will be 1, 0, 1, 1. When the input is 1, 1, 1, 1, 1, the output will be 1, 0, 0, 0. Now we can see the gray to binary conversion. For this we need 4 inputs and 4 output and we need 3 XOR gates. Now we can connect the circuit. This is the required circuit for gray code to binary conversion. Now let's check its input. When 0, 0, 0, 0, when the input is 0, 0, 0 and 0, the output will also be 0, 0, 0 and 0. When G0 is equal to 1, the output B0 will be 1. When G1 is 1, the output B0 and B1 will be 1. When both G0 and G1 is 1, the output will be B1 will be 1. When G2 is 1 and the others are 0, the output B2 and B2, B1 and B0 will be 1. When the input G2 and G0 will be 1, the output B1 and B2 will be 1. When the input G1 and G2 is 1, the output B2 is 1. When the input G0, G1 and G2 is 1, the output B0 and B2 will be 1. When the input G4 is 1 and the other one is 0, the output will be B0, B1, B2 and B3. All of the output will be 1. When the input G0 is 1 and G3 is 1, the output B1, B2 and B3 will be 1. When the input G4 is equal to 1 and G1 is equal to 1 and the output is 0, the output will be B3 and B2 will be 1. When the input G3 is 1, G0 and G1 is 1, the output B0, B2 and B3 will be 1. When the input G4, G3 and G2 is 1 and others are 0, the output B3 will be 1. When the input G4, G3 and G2 is 1, the output G0, G3, G2 and G0 is 1, the output B3 and B0 will be 1. When all the inputs are 1, the output B1 and B3 will be 1. This is known as Greco to binary converter.
Let's move on to the fourth experiment, design and implementation of code converter 2. First of all, let's see binary to XS3 converter. For this, we need 4 inputs, 4 output, 2 OR gate, 1 AND gate, 2 XOR gate, and 2 NOT gates. Let's connect this circuit. So now we had joined all the circuits. Now let's see its output. When the input is 0, 0, 0 and 0, the output will be 0, 0 and 1, 1. When the input is 0, 0, 0 and 1, the output will be 1, 0, 1, 1. When the input is 1, 0, 0, 1, 0, the output will be 0, 1, 1, 1. When the input is 0, 0, 1, 1, the output will be 1, 1, 1 and 1. When the input is 0, 1, 0, 0, the output will be 0, 1, 0, 1. When the input is 0, 1, 0, 1, the output will be 1, 1, 0, 1. When the input is 0, 1, 1, 0, the output will be 1, 0, 0, 1. When the input is 0, 1, 1, 1, the output will be 1, 0, 0, 1. Now we can move to XS3 code to binary BCD code converter. The requirements are 4 input gate, 2 AND gate, 2 NOT gate, 2 XOR gate, 2 OR gate and 4 output gate. We can connect the circuit. So we had connected all the inputs. Let us see its output. When the input is 0, 0, 0 and 0, the output will be 0, 0, 0 and 1. When the input is 0, 0, 0 and 1, the output will be 0, 0, 1, 0. When the input is 0, 0, 1, 0, the output will be 0, 1, 0, 0. When the output is 0, 1, 0, 0, when the input is 0, 1, 0, 0, the output will be 0, 1, 0, 1. When the input is 1, 0, 0, 0, the output will be 1, 0, 0, 1. When the input is 1, 0, 0, 1, the output will be 1, 0, 1, 0. When the input is 1, 0, 1, 0, the output will be 1, 0, 1, 1. When the input is 1, 0, 1, 1, the output will be 0, 1, 0, 0. When the input is 1, 1, 1, 1, the output will be 0, 0, 0, 0. Let us move on to the fifth experiment, design and implementation of parity generator. The required gates are 4 input gate and 2 output gate, 2 XOR and 1 NOT gate. Now let us connect the circuit. The outputs are when the input is 0, 0, 0, when the input is 0, 0 and 0, the output of odd parity is 1 and even parity is 0. When the inputs of 0, 0 and 1, the odd parity is 0 and even parity is 1. When the input is 0, 1, 0, the even parity is 1 and odd parity is 0. When the inputs are 0, 1, 1, the odd parity is 1 and even parity is 0. When the inputs are 1, 0, 0, the odd parity is 0 and even parity is 1. When the inputs are 1, 0, 1, the odd parity is 1 and even parity is 0. When the inputs are 1, 1, 0, the odd parity is 1 and even parity is 0. When the inputs are 1, 1 and 1, the odd parity is 0 and even parity is 1. This is the design and implementation of parity generator. So let's move on to the sixth experiment, design and implementation of multiplexers and demultiplexers. There are totally 6 inputs, 4 is data input and 2 of them are select input and only one output. The required are 5 AND gate and 2 NOT gate. Let's connect the circuit. So we had connected all the inputs. The output is when the input is 1, 0, 0, 0 and 0, the output will be 0, 0 and 1. When the input is 0 1 0 0 0 0 0, the output will be 0 1 0. When the input is 0 0 1 0 0 0 0, the output will be 0 1 1. When the input is 0 0 0 1 0 0 0, the output will be 1 0 0. When the input is 0 0 0 0 1 0 0, the output will be 1 0 1. When the input is 0 0 0 0 0 1 0, the output will be 1 1 0. When the input is 0, the output will be 1 1 1. Now let's look up the demultiplexers. For this experiment, we need 3 inputs, 4 outputs, 2 NOT gate and 4 AND gate. Let's connect this input. We had connected all the inputs. So let's check this output. When the input is 0 0 0, the output will also be 0 0 0 0. When the input is 1 1 0, the output will be 0 0 1 0. When the input is 1 0 1, the output will be 0 1 0 0. When the input is 0 1 1, the output will be 0 0 0 0. When the input is 1 0 0, the output is 1 0 0 0.
Hi all, let us see the seventh experiment of digital system design and implementation of encoder and decoder. For this experiment, we need 7 inputs, 3 OR gate and 3 outputs. From each input, we need to connect with the OR gates. For that, we need from the switches, one we need to connect to the third input of OR gate, and from each of the circuit we need to connect to the OR gates. And if we set the input as 1 is turned on, the lights of XOR gate 3 will be turned on. When that is 1 0 0 0 0 0 0, the output will be 0 0 1. When 2 is turned on, when 0 1 0 0 0 0 0, the output will be 0 1 0. Like that, for each switches that will be open. It is like the truth table of encoder. Now let's see the decoder. This is the logic diagram for decoder, which requires 3 inputs, 3 NOT gates, 3 input NAND gate and 4 outputs. When the input is set as 1 0 0, the output is 1 1 1 and 1. When the input is all 0, the output will be 0 1 1 and 1. When the input is 0 0 1, the output will be 1 0 1 1. When the input is 0 1 0, the output will be 1 1 1 1. When the input is 0 1 1, the output will be 1 1 1 0. Let us see the last experiment of digital system design, experiment number 8, study of flip-flops. Now this is The logic diagram of this is a circuit diagram of D flip-flop, which to eliminate the undesirable condition of indeterminate states in SR flip-flop, when both inputs are high at the same time, in the D flip-flop the inputs are never made equal at the same time. This is obtained by making two input complements of each other. This is the circuit diagram for JK flip-flop. The indeterminate state in SR flip-flop is defined in JK flip-flop. JK flip-flop inputs behaves like S and R inputs to set and reset the flip-flop. The output Q is added with K input and the clock pulse. Similarly, the output Q is added and J input and the clock pulse. When the clock pulse is 0, both the AND gates are disabled and Q and Q dash output retain the previous values. When clock pulse is high, the J and K input reads the NOR gate, which both the inputs are high, the output toggles continuously. This is called race around condition and this must be avoided. Thank you.